Okay, so we'll just start recording. So today's guest is Terry Zhu, who is at Monash University. He is a PhD candidate in computer science there, and he's also appointed at the CSIRO's Data 61. For those of you who aren't Australian, probably none of that makes any sense, and I'm sure that Terry will explain all of the moving pieces for us. His talk is going to be about BigCodeBench, which is about benchmarking code generation with diverse function calls and complex instructions. It's a critical part of learning more about large language models, and I really appreciate Terry's time in sharing his work with us today. Thank you, Terry.
Yeah, thanks for having me. So basically, I'm Terry, and the first-year PhD student at Monash, and also a part-time research engineer at the EACL. I'm also visiting at Singapore Management University right now, and also I'm part of the team of BigCode and leading the effort of BigCodeBench. So the work I'm gonna present today. Okay, so let's get started. So basically, today I'm going to present the BigCodeBench. So a year-long benchmark for code generation led by the whole BigCode community. So it's just I would say it's just the next generation of the human-able benchmark, if you heard of it. But let me just firstly quickly recap a bit of what's the kind of the recent progress of the code large language model. What does the recent code large language model look like, for example? So firstly, we'll introduce a bit of a stakeholder. So it's just another large language model of code built by the BigCode community before. So it's just last year. And then we basically collect a massive source code from the GitHub, specifically from and then build the stack, which is a well-known data source for coding right now at the moment, and it contains 6 terabytes of permissive code data. And we do a lot of filtering and cleaning, but I mean, it's just based on some rule-based method and also some human inspections. And then we collect it in the stakeholder data. So it contains a subset of the stack data, and which covers like 86 programming languages. And also we train the stakeholder base on this subset, and which contains like 1 T of the training data tokens. And also we further fine-tune it on the another Python subset, and then we call it stakeholder. And also, so in the meantime, we have another model from Meta AI. So they train a model called Llama, so which is a family of 3 models, specifically 7B, 15B, and 34B. So they utilize the previous versions from the Llama 2 of the same kind of architectures. And also they continue pre-training on Llama 2 on code and nature language specifically. So they have a better understanding of nature language as a consequence. So, and also they have 2 versions. One is called Llama, and the other one is called Llama Python. So basically there will be a slight difference because one is directly pre-trained on multilingual code data. Another one is then also fine-tune a bit on the Python code specifically, because like most of people now use like Python, I guess. So they just want to also do another Python specific code Llama, which definitely performs better on Python spin. And also, so nowadays, like there was a trend like using DeepSeek models. So they're like DeepSeek is a startup in China. So, and also they like kind of build a lot of models, including Mass, Coder, or the recent version 2 chat, and also version 2 Coder. So, but I will firstly introduce a bit of the version 1 DeepSeek Coder. So it contains 3 models specifically. So 1.3 billion, 6.7 billion, and 33 billion. So it stops the Llama 2 architectures because Llama 2 is kind of like widely used architecture nowadays. And also they do the same training data as stockholder. So, but they actually do like a lot of other kind of planning. So it can like covering some concatenations of the dependent files to form a single training examples that helps models to earn better on the more long context understanding, and also they train models on like more data specifically. So and DeepSeek Coder like kind of like performs better than the previous stockholder. And yeah, so that's pretty like kind of the recent progress of the called large language model training. So and also, so if you notice that like people now using are now using some of the benchmark like human eval or MMPP, but these models specifically can perform well on those benchmarks. So I mean, like for example, you will notice that from 2020, so there are not like many models, like, but there are like basically it started at the point of the appearance of the codex, and also upon that there will be a lot of more models coming up. So recent models like containing like stockholder 2, Llama 3, or others. So these large language model nowadays can do better coding. And also there's a trend like kind of saturating the human eval benchmark. So at the point of the end of January, so like I mean, if you can see the plot on the right hand side, so stockholder stockholder is not like kind of saturating, so it's just like having the performance of like 30% of the pass eval like pass rate at one. So I just want to a bit introduce about the like pass rate at one. So basically, like human eval contains like 164 tasks. Like these kind of tasks is function level, and to assure whether the model can generate the good solutions for these program tasks. So it is paired with a set of unit tests. So or just simple test assertions. So specifically, it's provided the pairs of like inputs and outputs. So if like we send an input, pass it into like model generate programs, so it has a output. So we assert whether this output is the same as ideal output in the ground truth. Then we calculate like the pass rate. So basically the pass rate means that whether models can specifically pass that task. So if like all of the test cases can be passed for one task, we count at one. So which means this can be successfully passed. And then we have the pass rate at one. So one means basically model will generate just one solution for each of the tasks instead of like more than one samples, because basically they like due to the efficiencies, we want to make the models generate one task and like one sample per task, because like it just saves the time, saves the budget. And then usually people are using the greedy decoding. So which means that when model generates a programs or any of the text, so it will be deterministic. So it's then basically it is safer to say a model can like have a kind of deterministic performance when generates just one sample per task. So then basically, if you notice that, so it's just at the beginning of this year, so it's just reaching 80% for most of the open models. And so last month, so when Cloud 3.5 Sonic came out, so if you notice, so they have a much better performance now, like widely used benchmark, including human eval. So on human eval, so they reach 92%, so which is the state of our performance right now. Yeah, so basically it's just saturating whole things. So and one concern is that like human niveau or MPP, these kind of algorithm specific benchmark are now contaminated in the training data. So basically, models were trained on that, so they can perform much better than the previous models. And now I just want to illustrate a bit what like specific the appearance of these kind of data set look like. So for example, human eval. So basically it's just kind of like have a short dot strings in a function level. So it just asks model to generate the solutions to complete that task. So, and also it's just algorithm specific. So basically it has some of the complexity in the completion, but it ignores any of the tool use, specifically any of the APIs from the libraries. So now these kind of libraries are commonly used by software developers and it's more realistic, but human eval doesn't contain any of it. And so ODEX. So ODEX is another benchmark focusing on the open domain code generation. So it just asks model to have a kind of one-liner solutions to utilize some kinds of library APIs. So based on the comments provided in the function. But notice that it's just a wrapper based on the previous another data set called Konala and also another multilingual Konala, which are basically the data set for natural language to API generations. But like ODEX step further on it, and then they do the like wrapping around these kind of API generations. So they wrap it in the code, like a function level code, and then they pair with some of like test cases so that it can better evaluate the model whether they can generate the correct API solutions or not. But it's pretty simple, but it just covered more tools. And also, if you notice, so there was another benchmark also kind of widely used nowadays called DS1000. So it has a set of programs ranging around like from different kinds of domain specific Python libraries. So they emphasize specifically on NumPy, Pandas, or TensorFlow, Scikit-learn, and the basically 7 libraries separately for different tasks. So for example, in this one, so they emphasize a bit of on the Python libraries. So, but they didn't specifically ask model to generate or utilize any of the API method. But this is the kind of class like object specific method here. So it just kind of locate and to do some of the locations to like kind of decide whether it is kind of having a yes based on the comments or just a task descriptions, and then to manipulate the solution itself, and then made models to generate the whole things. They have paired with a small set of the test sets specifically, and then to generate whether the model can pass the test sets based on the pass rate at one. But as you can see, so the prompts given to the models is pretty noisy. It's just kind of like based on the nature format. It's not like in the code format. So it just retrieve from the Stack Overflow questions. So you will notice that there will be also some of the noisy, more noisy prompts contain some of the error logs or like error generated by the terminal. So these kind of like logs are not helpful for any of the solution generations and more affected like for the model solution itself. So then if you notice, so the best performance on data science DS1000, DS1000 is not that high. So it's just near 50% of the accuracy for the best models. But yeah, it is kind of good regarding the coverage of the tools, specifically API use, and also the complexity, but it's not that high compared to the human eval. So then we introduce a bit of our benchmark, BigCodeBench. So specifically, we use one example to do that. So we have a pretty long context. So it contains more detailed instructions, but we don't want to emphasize any of the like low-level implementations. Specifically, we ask like the model based on some of the high-level instructions, but we provide more detailed ideal manipulations, how it should be done. So for input and output, and also we like let models to rate some kinds of errors for some of the tasks. So this trains the models to do more error handling or instruction following based code generations. And also we've emphasized also on the library usage or API usage. So we choose different combinations of the libraries and make it more open-ended, which means that models can choose wherever the APIs from these libraries or modules and to handle the task solutions and complete it. So we are not limiting any of the APIs specifically in the prompts or the doc streams. Yeah, so basically it has a good coverage of different libraries and APIs. It has a better complexity than the like what it use human eval, for example. And we also have like compared with other kinds of now existing code benchmark, specifically on the function level, which definitely like it's more efficient to benchmark the model capabilities of programming. Yeah, that's pretty much of the overview of different data sets, including the BigCodeBench. So, and also we like dive deeper into the design of a BigCodeBench. So specifically, we use one of the task structures as an example. So we pair with like a kind of a prompt covering the import statements and also a function name and also a part of the doc strings. So these doc strings are fine-grained. So we highlight with different parts of it, like parts of the things in the doc string. For example, we detail the parameters in the doc strings. And we also introduce about what's the specific returns it should be done for the values of basically instruct the model to have a better understanding of what should be done during solutions. And also we have a bit of the error raising or raise specific errors when specific scenarios happen. And also we have like some requirements and just recap about of our import statements. Just make sure the models will utilize these stuff for libraries instead of any of the libraries outside scope. So then it will just make them whole solution fail because we don't have any support of our unrecognized APIs or libraries. And also we have some examples just help models to understand better what should be done in the ideal way. So their model can better understand what way should be done based on some of the running examples in the Python interactive sessions. We pair with a kind of test harness. So instead of like just kind of input-output pair assertions, we have a set of like tests wrapped in the unit test. So we need to set it up because we have a kind of complex environment there. So we have to let models to kind of connect to the whole like operating system. So we need to set like, for example, set up the whole things about what is the specific like address ports for model to connect, and also some of the things we need to set up in the whole environment. So we have a setup method and teardown method to set up all of the configurations and then remove it when the tests are finished. So we tested different things in the unit test. So it's more complex than merely the input output. Then it covers a bit of the like multi-hit test. So specifically, we can mark some of the values during the like running procedures, and then make models to receive it, and then to test it whether model can have a good solution to output the correct or ideal outputs. So yeah, so and also basically the doctrine instruction is pretty complex, so we emphasize it just have more needs of composition reasoning. So it's asking models to actually reason about what should be done step by step, utilizing different kinds of APIs as tools to solve these problems. And a part of it, so if you notice that previous task descriptions is based on the code, specifically ask model to do some completions based on the task prompts inside of a code format. But in the real world cases, specifically considering like dial system or in a ChatGPT web-based, so you may ask your problems specifically in a nature language. So then is the time basically to ask the model in a more natural way. So you will transform kind of like complete prompt that we call in the complete split, and then we transform it into the instruct split. So which make the prompts in a more natural way. And specifically, we omit a bit of the more detailed descriptions because it just makes the things more natural, because you don't actually write a complex natural language in English, for example, to detailing all of the whole things like step by step. So we just emphasize a bit of descriptions of what should be done for the error raising and what should be done for the returns. Then we start with a kind of like code prompt that prompts model to generate a solution based on the task, the prompt we have here. And then we introduce a bit of our construction framework. So it contains 3 steps, but it just utilizing the whole large language model and put human in the loop. So then human can collaborate with large language model and to achieve the better task quality. Specifically, we start by data synthesis. So we synthesize the data and then do some enrichment based on the previous ODEX benchmark, because ODEX covers quite a lot of different libraries and API usage. So then we use kind of simple tasks and then like doing the enrichment by GPT-4 and generates a more complex task, having more complex instructions inside of docstrings, and then we collect these kind of raw synthesized programs in this step. But we also consider about some of the mitigations or bias, because we don't want models to have any of the take any of the advantage of their generated programs. So we do some of the function name authentications, and then we replace this kind of semantic rich function name with some dummy names. As we see before, we replace it with task bound, which is a like semantic doesn't contain any of the semantic meaning actually. And also we have another perturbation method, specifically perturb the whole nature language in the doctrine part. So we use another framework, NLL augmenter, to basically perturb the whole things and then make sure it has similar semantic meaning, but just like paraphrase the whole things a different way. Yeah, so that's pretty much the first step we do. And the second step, so we do about more like automatic program refactoring and also test case generations. So we have grounded the models inside of the code interpreter sessions. Basically, that's the simple sessions supported by previous ChatGPT models. And also we engage certain annotators. These certain annotators have like more than five, like most of them have like more than 5 years of experience in Python, and also most of them has a PhD in computer science. And also we make sure these annotators are like the authors, because we want to acknowledge their contributions specifically for our BigCodeBench benchmark. So, and we design a kind of long context documentations, and also we detailizing what should be done for human aspect, and also what should be done for a large language model aspect. And then we make sure all of these kind of annotators understand what should be done for each of a part. So they need to provide specific instructive feedback to the models. And then because they are not like, because adding like writing the test cases from scratch for like unknown programs definitely challenging. So we utilize the large language model to ease this process. So basically, instead of manually like adding or refine the programs or catching bugs inside of it, we let models do that. And then, but we provide some of feedbacks where like human annotators getting more familiar with these kind of tasks. And also, we have different constraints of how model should generate or how model should perform these kind of refinement, and also how it should be done for the test case generations. And also after we collect all of the past test cases with the corresponding refined tasks, and also we have the third step for human curations. Then we have a bunch of annotators from previous step to examine whether the model generated or model refined task like requires the like meets the requirements of different parts of the specs. For example, if it's utilized like more than at least more than 2 libraries, or whether it's like kind of natural based on the human understanding, or whether the formats of doctrines meets the requirements of the like common practice, or whether the contents align with the test cases, or whether the doctrine align with the solution itself. And then we make sure everything is PyTest compatible, so then we can run it and deploy it anywhere else. And specifically, we later we could utilize the GitHub container to do the deployment, to actually celebrate a action, automatic actions, basically kind of rerun the whole test cases against the like task solutions. And we do some of the pre-evaluations. Specifically, we utilize the GPT 3.5, which is different from the like GPT-4 we used before. So then we actually kind of evaluate these models on different tasks we have, and to assess whether there will be some misunderstanding of the GPT-4, GPT 3.5 because our curations, or we need to do any of the further refinements of these tasks. And then we basically finish up the whole process like in 1 year, because like people have their own business to do, and also it's pretty exhaustive to like actually collect more than 1,000 programming tasks involved. And I just want to also introduce a bit about our statistics or the benchmark, to highlight a bit like how complex it is, how diverse it is. Specifically, so as we can see, so we have more tasks in overall compared to either human eval or ODAX or DS plus also. So we have also a better coverage against like the ground truth solutions, so we should achieve an average of 99%, having more like 5.6 tasks on average. And also our prompts definitely longer than the previous benchmark, also same as our solutions. So we have like, which means that we have like kind of like more complex implementations required for model to complete these tasks. And also, so it covers more diverse tools. So we have different kinds of domains. So that I will illustrate later. So we have like 7 domains, and also about these 7 domains, we have different kinds of libraries, 77 from the standard Python libraries and another 62 from the external libraries. We make sure these kind of libraries covered is widely used by according to the Python index download statistics. And also we covers a lot of different calls according to the ground truth solutions. And basically on average, each of the tasks requires more than 2 nearly 3 libraries usage, and also more than 4 function calls to complete the task. So we have different combinations of different libraries, different functions of different domains. So it's just much more diverse than the previous like data sets for benchmarks. So we also share some of the examples of different domains we covered. So we specifically covered 7 domains. So computations, more general domains, visualizations, system, time, and network, and cryptography. So the percentage here actually presents there are 63% of the tasks having computation libraries, or 44% of the tasks have general domain libraries. So any of these kind of libraries will be more familiar with it, and also they are pretty common to see. And then we have different corresponding APIs from these libraries. Yeah, that's pretty much the status. And also we introduced about our evaluations and findings. And also, so based on our previous introduction, we have a pass rate as our main evaluations for different whole generative benchmark, and same as our BigCodeBench. So we utilize the greedy decoding to do it. So we set the k equals to 1 because it's just make the whole generations evaluation more efficient. But we utilize the calibration setup, because we notice that when model generates the solutions specifically in the instruction tune way, or you the setup in the chat template in large language models, so they follow the instructions specifically to complete a task. So in that way, some of models will appear to be more having some more laziness compared to other language models. They will constantly omit some of the essential details in the completions, which leads to the failure of model completion. It's not because of the capability of models, but just due to the laziness of model itself. So we utilize the calibrations to actually add those missing details in the code prompts back to the solutions, and make sure model can basically bypass any of the omissions because of its original completions. And then we have different findings, for example, like instruction tuning how to follow programming constraints. It's definitely more kind of intuitive, and also the large language more sensitive to the verbosity of the programming instructions. Specifically, we discussed the performance gap between the complete split and the instruct split. So because in the instruct split, we have less verbose programming instructions than the complete split, because we actually drop off some of the detailed instructions. And also we have different domain-specific findings. So specifically for top models, they can perform well in different domains, but some of the domains they can't perform the best. So that's what I mean here is jack of all trades, master of both. And also large language model can use different function calls to solve the task. So by nature, because we don't constrain the model to do any of the invocations for specific APIs. So we let them to choose whatever APIs they want. So we have found diverse usage of these kind of function, any of the function calls from the specific modules, specific libraries. So they can use different things to solve a task successfully. So we provide and we host a whole live leaderboard. We are constantly updated. So far the best performance still GB4O based on these 1,000 more than 1,000 program tasks. And also we have the ELO rating. So basically we follow the previous setup in live the chatbot arena. So we do some bootstrapping about our bootstrapping of our performance among different models, and we would treat each of the tasks as a game. Basically, we have a winner or the losers for each of the tasks, considering whether they pass the task cases or not passing the task cases. So when it's tied, we exclude it. We only consider the winner. So then we do these kind of a rating mechanism for our benchmark, because it have a more can distinguish different models from models. Specifically, you can have a kind of tier 1, tier 2, and some of models perform similar to each other, and some models not. So for example, GB4 definitely is ranks the best, and the second tier actually close to the GB4O is DeepSeek Coder. But then for the third tier, like Gemini, GB4 Turbo, or GB4, they perform much similar to each other. And we have a visualizations of different solve rate for different tasks specifically. So we have different two splits. So one of is the BigCodeBench complete, another one is instruct split. So we have different performance of these two splits, and we calculate for these evaluate models what's the average of the solve rate for each of the tasks. So, and also we calculate the lowest upper limit, which means that each of the tasks should be solved at least by one model. So according to that, we have a much higher upper limit, but no models by now can actually achieve that upper limit so far. Yeah, so, and we highlight a bit of the broader impact. For example, we have a wide collaborations, actually international collaborations with different institutes, and also our BigCodeBench previously was on the training list of the Hugging Face dataset. So same as our BigCodeBench leaderboard, it's highlighted by different podcasts, and also hosted by a hackathons. Specifically, some of the engineers are kind of doing prompt engineering for models to achieve better performance on our benchmark, but so far they can't do it. And best models, best performance they achieve are also around 60% for some small models. And also, it's just mentioned about the in the other articles, for example. So we'll just also highlight a bit of what's next, step, or what's the next stage of BigCodeBench. So we will continuously develop BigCodeBench for sure. So for example, we asked some of the questions. For example, how can we make BigCodeBench more realistic, challenging, efficient to use? And we highlight a bit about the recent work like MixEvo. So they actually mix different existing benchmark samples to have a more efficient way to evaluate the model performance and then align with the ranking of the chatbot arena. So, but their cost is pretty low. It just kind of like averagely $0.6 to evaluate the mix, like for example, mix equal hard. And their step is doing some of the query collections and then to see how they can align with these queries for the existing benchmark samples. And then they do the alignment and then doing some sample selections based on this distributions. And then they set up the mixer eval hard to actually make it a subset of the mix eval, and also make sure it can be dynamic because it's based on the query versions they select or they source in the previous step. So they can keep updating it. So we consider this is a good approach. So we actually introduce a bit about our hard subsets, for example. So BigCodeBench have different concerns, potential concerns actually. So one is about like it's not kind of like imbalance scenarios because it have different domains, different scenarios. So it results in more inaccurate rankings. And also, for example, the best performance is still around 60%. It's hard, like some of criticism can be like, it's not hard enough. And also 1,000 tasks can be too big and the evaluation times will increase significantly. So we will introduce a hard subset, which actually is planned to release by the end of this week. So we have a Stack Overflow queries as our queries because it covers different kind of programming tasks, but just request by the real world human developers. So we actually compute the sentence embeddings of these queries along with our BigCodeBench tasks. So we do some of the alignment and choose the top one BigCodeBench task of the tasks like Stack Overflow embeddings, and then we do some filterings, and then we collect the BigCodeBench hard. So as based on our preliminary explanations, we found out our rankings, especially for some of the represent models, are pretty aligned with the Scale AI's, the Reason Seal leaderboard. So they have a coding leaderboard specifically. So we compare with it. We have we found out the ranking is pretty aligned. And also we have asked other questions. For example, nowadays models are overfitting on the Python. So how can we do it? So basically, we'll extend to the multilingual code generations. For we will consider some of the programming languages like Rust or TypeScript or JavaScript. So how we can actually utilize these language models, these language models to do code generation on more kind of less overfitting programming languages. So we have different constructions process more different from the existing construction method, because nowadays there are two major ways to construct the multilingual code generations. One is the actually it's a closed domain. So closed domain code translations, they can translate, for example, the human eval to other programming languages. For example, JavaScript or Java or C++. So there's a benchmark specifically built upon this called multi-PLA. So they do the code translations and then actually propose a multilingual code generator benchmarks upon some of the algorithm questions. Another way is direct collections from multilingual online judgment platform, because LeetCode or Codeforce, so they covers different kind of programming languages. So they support different payouts for solution submissions. So they can actually collect these kind of multilingual solutions based on each of the same task. So then they can construct multilingual versions of the code generation benchmark, but they are pretty like close domain because they only focus on algorithm specific question. So challenge for the BigCodeBench is like there was no one-on-one mapping for program language specific packages or libraries. So it's definitely correct before because different programming language have different paradigms. So like for example, Python will emphasize more on like data science or machine learning or AI or any of the backend paradigms. But some of like JavaScript, TypeScript are not. So even though they can do a bit of a backend, so but most of it will support on the web development, which will be a kind of like different from the Python main usage. So we actually propose different pipeline to actually construct such kind of multilingual BigCodeBench. So we will collect a list of libraries and then actually also collect the list of the library documentations. We'll utilize some of the ways to do some mixings of these APIs from different libraries documentations. So then we prompt models for like actually synthesis, doing some program synthesis, and also with the test cases. But we're also iteratively doing some filtering based on the compilations, executions, or human inspections to actually clean any of the noisy or like failed programs or tests, and then we will basically collect the final stage of a clean samples there. But it's just work in progress right now. So we will keep exploring how we can enhance this pipeline specifically. And for example, and also we ask another questions in different directions. So of how we can make the BigCodeBench more rigorous. And then we like highlight the previous work, like the EVO Plus, which is a framework that is now widely used for Human EVO Plus, MVP Plus. They actually increase the rigorousness of the test cases. So they actually emphasize the previous existing Human EVO benchmark, for example. So the test case is not that rigorous, and some of the test cases can be bypassed the model solutions, even though the model solution can be incorrect. And they utilize a whole kind of mechanisms to do some mutations, like testing and differential testings, and then to make sure they can generate a long list of like input output pair assertions for test cases to actually make the benchmark more rigorous. So we announced a collaboration with the EVO Plus team. So because writing tests, like good tests is hard. For example, BigCodeBench may contain some weak tests. It's like not specifically aligned with the instructions, but model can easily bypass these kind of tests. And some of the tests may contain some flakiness, or some of the tests will be more overall specified, because some of the instructions may just, it requires one spec, but the test cases may require more specs, for example, which is not covered in the original instructions. So we want to make sure that basically the test cases are more aligned with the instructions, and also test cases are rigorous. So we propose a way to actually do it, but it's also work in progress. So we actually prompt the models with different programs, solutions generated by different models, and then we prompt with the task prompt, for example, and with that model, it generates the new inputs, for example, and then but based on each of the model generates programs, we have another set of new outputs. So based on that, we'll do some comparisons. It's similar to the differential programming. So, and basically we can make sure, for example, if they are not aligned, like the output is not kind of the same. So which means at least one of the programs has bug. So we can actually detailing what actually is going on with the test cases. So we can make sure there can be improved by adding some of the better test cases. But if it's like kind of correct, then it probably means that the general like programs against existing test cases are pretty good. So we don't need to add any of the more test cases so far. And also, for example, we also ask another question. So do large language model really understand BigCodeBench tasks? So because we highlight the realness of and the complexities of the BigCodeBench, like compared to other coding generation benchmark. And then we also highlight a bit of previous word like proxyable. So proxyable is a benchmark specifically like assessing whether the model can reason or understand the execution process of the kind of easy programs, right? So given a kind of easy programs, pretty straightforward. So they assert whether model can doing output prediction specifically based on a simple input or based on the output, whether they can do the predictions of the input. And so far they found out better models definitely have better performance. For example, G4 Turbo can achieve more than 70% of pass rate at one by utilizing chain of thought. So which actually help the models to actually doing some step-by-step more synthetic ways to reason about the programs, and then it just aids the model performance and boosts the whole quality of the predictions. So they have a better performance when adding chain of thought. But original GPT-4 can also do well, nearly 70% of the pass rate at one. So which means that kind of it's not that high enough. So how can we actually build a probably harder benchmark, more challenging benchmark? So we can utilize the BigCodeBench. So we are also collaborate with the proxy team. So specifically, we'll explore how well do large language models understand practical programming instead of previous pretty straightforward algorithm specific programs. And also we will explore whether in this case does chain of thought help or does fine tuning help. So this is kind of the things we will explore in the next stage. And also, we will continuously do some of the incremental data refinement. We can improve the data quality of the BigCodeBench step by step, and we will continue to do some of the software development. So to support the evaluations, executions for the model evaluations, for example. And we will actually make the evaluation more agentic, which means that we will actually run the models in interactive sessions, like any of benchmark SweetBench or other benchmarks that requires the model to interact with the environment. So we can put it in a sandbox, and then we can request the model to do self-repairing, self-reflections to actually improve their quality or performance on these tasks. So we also can assess a bit about the generalization capabilities. So considering that now BigCodeBench covers a lot of common libraries, common APIs, how about the performance on unseen APIs, unseen libraries? For example, models, a lot of models may not kind of train with the data covering long chain llama index, but how well language model can do the generalization on these unseen libraries. So we can do some RAG-based evaluations to assert whether models can better understand based on a given documentation to generate or solve the task for these kind of domains. And we will build the next generation of models to utilize function calling with the coding. So as you might see, for most of the function calling works nowadays, they emphasize about the RESTful APIs, which is the HTTP API usage. So most of them emphasize about the correctness of the argument passed to these kind of like functions, but it's not enough. So in the real world, so basically the program will utilize these function calling or HTTP APIs, also along with the other kinds of library specific function calling. So how we can make sure the models to combine the programming with this function calling to actually boost their performance about the the real world open-ended task. So it's another kind of directions we'll explore in the near future. Yeah, and also that's pretty much of the things about today's presentations. And if you're interested in our work, feel free to scan the QR code. And yeah, that's pretty much it. Yeah, thank you.
Thank you very much, Terry. That was absolutely fantastic. Are there any questions from folks? I'm aware that we're at the top of the hour, so we should probably finish up fairly quickly. But are there any sort of brief questions from people?
I've got a question.
Yep.
Far away.
So I don't do research in this space, so this might be a little naive. I'd be curious to know, beyond the ranking lists for evaluation, how does one go about understanding why the model is failing? Like how does one talk about and analyze failure cases beyond just which tests have failed?
Well, I mean, so we did a bit about our case studies in the appendix of our paper actually. So but in that paper, we still kind of explore how some of the specific tasks and also why kind of, for example, GB40 failed in it. And then we found out kind of the things is that we emphasize about our kind of test cases. Some of the tests include some flaky tests or over specific set of tests because it's kind of API related for market tests. So at this stage, model may fail, but some of things we found out majorly. So model can't put things piece by piece in the correct orders. So then fails for the overall completions. So it's not like model can't understand these libraries or APIs. Model definitely understand these kind of common thing libraries and APIs. So they can utilize one things at one time. But when they compile each other to actually make it more comprehensive solutions, they can't. So they will fail in some of the kind of small logics failure. So then just leads to the big mistakes of the whole programs. Then it just failed for the whole things. I guess that's pretty much the major things we found out when inspecting the whole failures of different model solution.
Mm-hmm. Thank you.
Yep, no worries.
Terry, can you talk a little bit how you deal with evaluation of code that is functionally the same, but looks a little bit different? Like, how do you actually evaluate the code that is generated?
Well, you mean so we can use a kind of example if you want.
Yeah, if you go back to some of your
well, actually, I can actually, for example, I will just do we can just bring up the data set right now. So since it's just kind of visualize the whole thing on or I can just do for example, I'll just do the viewer. I think this viewer is better because just give you the whole structure things right now. Oh. May takes a bit of time for space only. Well, it's coming. Okay, so can you utilize for example here, right? So this one is definitely easy. So we assert like whether they have a kind of like equal things or whether it's kind of range. We have like kind of weak test or stronger test to assert whether the things almost equal or not equal based on the task descriptions. For example, there will be a task mentioned about like calculate the average of sum of the absolute difference between each pairs of consecutive numbers. So for permutations of given list. So we kind of do the whole test cases wrap up in the test cases specifically based on the unit test case. And then we have sets of test cases to like kind of test different things, testing range or testing like kind of like specific values, a larger list with a seed to actually make sure it generates the whole things in the correct way. So we also set up a seed to actually specify whether kind of randomness is kind of deterministic. So then we can assert whether it's kind of good or not. So because we don't actually require the model, for example, do any of the random like C initializations. So but we will do it outside of the programs and then set it in the test cases. And also, so other kind of things. So I can do other things. So it's also the previous one is all kind of like easy. I can do some CSV, for example. So we will create the whole things. So we have a setup method or teardown method to create a whole like kind of like test like directions to create a whole CSV file. So what we mentioned and how we create the CSV. And then based on that, we will assert whether just return the good things or kind of expected things for each of the test cases or not. So we set up different kinds of inputs and for different like directories, and then we check whether model behaves correctly or not. For example, they will raise kind of like error, not found error, like file not found errors for when it is doing some of the unknown functions. So I guess that's also some of things we emphasize in the test cases. I don't know if this kind of answer the questions or not.
Very thoroughly. Yeah, that's incredible. Yeah, thank you.
Yeah, no worries.
Does anyone else have any other questions? All right. Well, it's getting late for you. Just briefly, Amin asked me to ask, are you able to share the slides or
Yeah, I can share the slide. So like I will just email you later via the email, like the link or something.
Yeah, that'd be great. Yeah, thank you.
No worries.
Yeah. All right. Well, it's getting late for you, so we will just say thank you once again, Terry, for a fantastic presentation, and thank you more generally for a fantastic contribution to helping us understand the state of LLMs. Really appreciate all your time, and very much looking forward to seeing what you do next. So,
Thank you.
thank you. Have a nice day, everyone.